All right. Okay. Now let's start talking about what we really care about is the error in the finite difference solution. Okay. So I'm going to use the elliptic equation as an example, but you're going to see the same thing applies to other equations. Not the same thing, but similar analysis can be done in other equations. Okay. So we are solving for the equation partial square u partial x squared equal to f. So this is the elliptic equation. It's called Poisson's equation. Okay. And we approximate the solution using AU equal to F. Okay. So here, usually we denote the analytical solution and the numerical approximation using the same letter, but in this case, because we are explicitly looking at the difference between the analytical and the numerical solution, we need a little bit different notation here. So let's say UI hat is the solution of the finite difference approximation. So that's the hat means it's a numerical approximation. And UI is the analytical solution, is equal to the solution U at xi. So this is a approximation, and this is exact. Okay, the approximation is also called the numerical solution. Okay, we are interested in the difference. So the error is the difference between the analytical solution and the numerical solution and the analytical solution. Okay. Now how do we get this error? Particularly if we can link this error in some way to the truncation error, then we have some way to analyze how big this error is. To do this, let's apply the same matrix to this vector E, where vector E is basically E2 etc. to En plus 1 is the vector of all these E's at all the grid points. So because it's a matrix, that can be applied to my U hat. This is actually hat minus A times the analytical solution U, right? So we know that A applied to U hat is exactly equal to F, right? So that is the definition of the approximation of the numerical solution. Okay, but we actually don't know what is A times the analytical solution is. So let's get into details of that. And let's look at this vector at the ith grid point. Okay, so yeah, let's look at the vector at the ith grid point. Okay, so for the first f, it is just fi, right? The function f at the ith grid point. Then minus, let's now write down what a is. A applied to the analytical solution is actually ui plus 1 minus 2ui plus ui minus 1 divided by delta x squared, right? That's our finite difference approximation. So this is actually the finite difference approximation applied to the analytical analytical solution. And the analytical solution, instead of the numerical solution, which we only know at the grid points, the analytical solution should exist as a continuous function. And we can apply Taylor series analysis to the analytical solution. Actually, we already done that This is the truncation error, right? This is the truncation error, because the truncation error is the difference between the finite difference approximation and the analytical second-order derivative of u. And the analytical second-order derivative of u is equal to f. All right? And that f cancels with this f. So this is just the truncation error. Agree? Anybody have questions on that? I mean, that's, yeah. We are trying to link the truncation error to the solution error. They are not exactly equal. You see, the truncation error is equal to A times the solution error. The solution error is difference between the numerical solution and analytical solution, while the truncation error is the difference between the analytical differential operator and numerical finite difference operator applied to the same analytical function. While the solution error is the difference between two functions. One is the analytical function, and the other is the numerical solution. They are completely different concepts. All right. And the truncation error is something we can analyze using Taylor series. We can't analyze the solution error using Taylor series. But the solution error is what we really care about. That is a direct measure of the quality of your numerical solution. Right? Now, this analysis tells us that A times E is equal to tau, where tau is the vector of, minus tau, is the vector of like all the truncation errors. This is a very important conclusion. Is the differential operator operated on the solution error is equal to the truncation error, or minus of the truncation error. And now we can see that having the truncation error being small may not be enough. We also need some good properties of the matrix A. Because an alternative is I can write the solution error equal to A inverse times the truncation error. If A inverse is something huge, then my solution error can be pretty large, even though my truncation error is small. I always forget the minus sign. So we need the A inverse to be small in some sense. Still linear, yes. Very good point. So, okay. So the question is, the matrix A is still linear. So the order of accuracy of tau still apply to the solution error E? Do we agree with that? Yes? Yeah? Exactly. So A is linear, but A is different for different delta x, right? Even the size of the matrix A is going to be different for different delta x. If you have a smaller delta x, you are discretizing the function into more grid points. You have a longer vector tau and longer vector E. So you have a bigger matrix A. So not only the entries of the matrix A is different, even the size of the matrix A is different. So the order of accuracy analysis in tau does not directly apply to the order of accuracy of E. In order for that to be applied, in order for the same order of accuracy of tau to apply to the E, you need something else. And that something else is called stability. stability basically means the norm. So the double absolute value thing is called the norm of matrix A. Okay. The norm of the matrix A inverse is bounded regardless of delta X. Okay, so what is the norm? What is the norm of a matrix? The norm of the matrix is the maximum ratio you can get. Is the maximum ratio you can get between the solution error and truncation error. Okay, so I mean the strict definition of the norm of a matrix, let's say matrix, is defined as the maximum possible ratio between the norm of m times a vector v divided by the vector v itself. So this is maximum is for any v. And the norm of a vector, how many people knows norm of a vector, like in linear algebra? So I suppose everybody knows the norm of a vector. So norm of a vector, in here I'm just going to write the L2 norm of a vector, right? Of a vector and also matrix. The L2 norm of a vector is equal to the square root of v1 square plus etc. plus vn square. It's just the Euclidean distance in some sense. Okay, and you have this. So the norm of the matrix A inverse defines the maximum ratio between the solution error and truncation error because the solution error is equal to the matrix A inverse times truncation error. And the norm is independent of the minus sign. Okay, any questions on this? The definition of stability. It basically means that if you have a small truncation error, you cannot have a big solution error, regardless of grid refinement. Oh, okay. So let's take a look at so first of all, how important is the concept of stability, and second of all, how do we get stability for the let's say for the Poisson's equation? Okay, so first of all, the relationship between consistency, stability, and convergence is the following. Stability we have just defined, and consistency means the truncation error goes at least order of delta x. It means as delta x refines, as delta x goes smaller and smaller, the truncation error goes smaller and smaller. Okay, so basically truncation error goes to 0 as delta x goes to 0. Okay, convergence means the solution error goes to 0 as delta x goes to 0. That's what we want. And if you have stability, then consistency means convergence. And also, you have the same order of accuracy for the solution error as for the truncation error. Okay, so that's a fundamental theorem in numerical analysis, numerical solution of differential equations. That is the critical link between consistency or order of accuracy of the truncation error and convergence, which is the order of accuracy of the solution error. It's this concept of stability.